next video in the IB Physics SL and HL series. Today we'll be looking at B.2, the greenhouse effect. Before I begin, I'd want to preface by saying that I don't think this topic is entirely physics related, and if you're looking to study for your exam, this should not be one of your priorities. And I'd say the only studying you really need to do is watch this video, because it's just a bunch of memorization, and that too, it's quite surface level, and there isn't really anything deep you need to know. So now let's just get into it. I'll talk about only what's essential here, and because this topic's not really that interesting, nor is it that important for the exam. So first, you need to know what emissivity is. It has a symbol E, not to be confused with Euler's number in math. And the units, there are no units for emissivity because it's power divided by power, which gives you a unit of 1, and of course 1 is not a unit. So emissivity is basically the radiated power, so the power released by an object, divided by the power released by a black body, where a black body is something that absorbs and emits radiation perfectly. So that's all emissivity is, and power here, what we remember is sigma a t to the 4 from the last video. All we need to do, if they give us emissivity here, we just need to multiply this value by emissivity. Emissivity is always a decimal because the power radiated by the black body is the maximum power. So whatever this is will be less. So emissivity is always a decimal. Now we need to look at albedo. Albedo basically means reflected or scattered power divided by incident power. And so it's just a ratio of how much power is reflected back by how much power is actually brought on. So if I shine a flashlight onto the ground, the bottom here would be the incident power, so how much power I'm shining onto the ground, and scattered would be how much reflects off the ground. So albedo is also a decimal because incident power is always bigger than scattered power. There's also no units again because it's power divided by power. So now let's look at the solar constant. This has a symbol S and units watt per meter squared. And a solar constant basically just means the average intensity of the solar radiation orthogonal. So orthogonal means perpendicular or 90 degrees to the Earth when the Earth is at average distance from the sun. So if you want to, you can memorize this, but I highly doubt this is going to come up on the IB Physics exam. And the solar constant is given in your data booklet, and it has a value of 1.36 times 10 to the 3 watt per meter squared. And the incoming power over the full Earth is S by 4. And again, you don't need to know the proof for this, but in case you're interested, it's just because you're doing pi r squared divided by 4 pi r squared. So you're doing pi r squared, which is area of a circle, divided by 4 pi r squared, which is surface area of a sphere. And that gives you 1 over 4, and you multiply that 1 over 4 with this S right here. So the incoming power over the full Earth at any given point in time has an average value S over 4. So that's it. And lastly, we just covered the greenhouse gases and the greenhouse effect. This is very simple. So the 4 greenhouse gases that you need to know are water vapor, carbon dioxide, methane, and nitrous oxide. So water vapor just means steam. So like if you're boiling pasta, you're creating water vapor, which is technically a greenhouse gas. Carbon dioxide, I'm sure you know what that is. It's like what pollution is pretty much. So a car exhaust pipe would release a lot of carbon dioxide. Methane is another greenhouse gas. This one comes mostly from like agricultural things, like for example cows. When they fart, they release methane. So that's CH4. And nitrous oxide. So funnily enough, nitrous oxide is actually illegal in most countries. It's a drug. You might know it as laughing gas. And nitrous oxide is also a greenhouse gas. So if you're environmentally conscious, don't do nitrous oxide. Or like, if you're anything, don't do nitrous oxide because it's a drug. But anyway, so that's all you need to know. And now the resonance model is basically a way about how we can think about the greenhouse effect. It just means the incoming radiation from the sun is absorbed. And we need to go a little bit deeper than that. But basically incoming radiation from the sun is either ultraviolet or visible light, and visible light is absorbed by the surface. So as you can see here, this is incoming and this is visible light right here, and this is absorbed by the surface, and this part is reflected. So this would be how you calculate the albedo of Earth, but here we just see what's absorbed here. So that's 161 or whatever it is. So this is however much is absorbed by the sun, by the Earth, and then basically this is what's sent back out. So right here, the greenhouse gases, the visible light is also re-radiated back and it becomes infrared. So this here is infrared radiation. It comes in as visible light and it leaves as infrared. And basically greenhouse gases up here somewhere absorb this infrared and then send it back to the Earth like this. And that's called back radiation. And because of this, it's once again absorbed by the surface. And so the temperature of the Earth increases because, as you can see here, when you absorb power, your temperature will increase. So that's pretty much the entire resonance model. Now there's something called a molecular energy model, but this is just the resonance model looked at a little bit deeper. So all it means is that the natural frequency of the greenhouse gases that are up here matches the natural frequency of the infrared that's coming up here. And so basically it absorbs nicely and then it reflects right back. So it just explains why. So that's all you need to know. And the last thing is that energy in is always energy out. You probably remember conservation of energy. So energy is conserved, and so Earth has an energy balance generally and ideally. So that means that if Earth had a perfect energy balance, then the temperature would stay the same. So this solar energy coming in, this plus this plus this plus this plus this is equal to this plus this plus this plus this plus this. So yeah, that's pretty much the entire of B.2 covered, and I hope this helped you. But again, I'd like to reiterate the advice that if you're looking to study for IB physics exams and they're closing down upon you, I would not prioritize this as a topic. At most, I'd just watch this video. I don't even think they ask any questions on this really generally. At most, it'll be like 2 marks or 3 marks across both papers. So yeah, that's all I think you should do. I hope this helped you, and have a good day.